Hi students, this is the last topic for Olympiad training. It's on special relativity. So I'll be going through some of the content of special relativity. Of course, I can't go through all. So to learn more in depth, please try some of the questions that I'll provide to you and read some of the textbook pages as well. So if you can see from our syllabus document, there's actually quite a lot of things to cover for relativity. But I'll cover the main basic ideas, which is the Lorentz transformations for space and time, and the equations for mass energy equivalence and the relativistic equations of motion. And we'll also discuss, the visible, what's this called, phenomena of relativity, which is time dilation, length contraction, the relativity of simultaneity, and of course, lastly, we'll discuss the conservation of energy and momentum for elastic and non-elastic interaction of particles. There's one point here, which is the relativistic Doppler effect. If I have time, I will try to draft out a extra document for you all to read on their own. So that's like, really advanced level. You have to have a very good understanding of all your H2 topics to be able to understand this, as well as some of the other Olympiad topics. But we'll see. All right, so what will we discuss today in Olympiad? Well, before Einstein, we have a very good grasp of classical mechanics. Humans understood mechanics very, very, very well. We understood how particles behave. We understood how waves behave. We had the equations to describe all of these. We also thought that space and time are invariant in the sense that, space is space, time is time. They are two different things. Objects move through space, and how we keep track of their motion is using an axis called time. And in order to convert from one observer to another observer's point of view, we use what we call Galilean transformations, right? Which is basically something like relative velocity that you have learned in chapter 1 for H2. Right, lastly, we learned about the generalization of curve mean. Oh, wait, that's a bit too much. So when Einstein came along, just after a few simple ideas, basically we had the special theory of relativity. So the special theory of relativity has just two very basic postulates, and then it warps all the classical physics that we know, and it leads us to phenomena such as time dilation, where things take different amounts of time depending on your frame of reference, the length contraction, where objects have different dimensions depending on who's observing them, and of course, instead of having your regular addition of velocities using Galilean transformation, we have to modify it, and the resulting method is just called Lorentz transformation. And of course, we got new equations for mass, momentum, and energy. Lastly, what you will learn in H2 and J2 is actually mass energy equivalence, where mass can be converted to energy and energy can be converted to mass. If you can do it, there is an equation that relates how much gets transferred to the other. So what we're studying is Einstein's theory of special relativity, and it's called special, but why is it called special, right? It's special because it is not general. So Einstein later on published his theory of general relativity, which is true in gravitational fields. So special theory of relativity is just the simpler form of relativity where we don't consider gravitational fields, we just consider objects moving in, regular space, right? So that's why it's called special. It doesn't have gravity. So in physics, one of the ways we actually describe motion is to measure with respect to some particular coordinate system. So I'll say, oh, this is the origin. I'll put a set of coordinate axes here. In the picture shown, this is a regular Cartesian coordinate. So from this coordinate axis, I can define the position of every other object in the universe. So for example, this little bat here, it's defined as x-axis 3, y-axis 4, z-axis 5. So this is one more axis than normal because we are dealing with three-dimensional space. So our bat's coordinate is 3, 4, 5. Of course, I don't have to choose the x, y, z axis that we just saw in the last slide. I could choose another set of axes, x prime, y prime, z prime, right? Then, basically, if I want to take measurements, I can say, oh, depending on which is my coordinate axis, the actual measurement or coordinate of the bat will depend on the choice of axis. So this is a relative choice. Depends on which axis you want to choose. Neither of them are wrong. It's just that the number will be relative to another. And if there is such a choice for us to choose coordinate axis, it must mean there must be a way to convert measurements in one axis to measurements in another axis. So this brings us to what we call the frame of reference. The frame of reference is like, oh, you know, I want to take measurements and I'm an observer. So I set up my laboratory in this measurement axis. So I will have to have a coordinate axis, and it allows all points in space to be defined at any instant in time. This is called a frame of reference. Right, so in Newtonian physics, we have our three spatial axes. What we are familiar with is the Cartesian coordinate axis, but we also got other types of axes that have three perpendicular vectors that allows us to define any position in space. You will learn them if you take more advanced mathematics in university, in engineering or science. They're called polar coordinates or spherical coordinates. Basically, it just makes your calculus easier depending on the types of equations you have for the topic. Alright, and the symmetries of your problems. And in special relativity, each frame consists of a three-dimensional spatial axis and a one-dimensional time axis. Right, and if you plot them out, basically you can plot all space axes as a flat two-dimensional space axis. We call that the hypersurface of the present. And if you plot out the past and present of time, what you can get is a three-axis where two of it represents space and one of it represents time. Then a horizontal slice right through the origin would just be what we call the hypersurface of the present, and anything above in positive time is in the future, and anything below the hypersurface of the present in the negative time axis is the past. So I'll leave out the discussion on future light cone and past light cone after we discuss, you know, the postulates of special relativity. Right. So we have discussed frames of reference. Basically, any coordinate system can be a frame of reference, right? However, there's something special called an inertial frame of reference. So an inertial frame of reference, right, is a special frame of reference where Newton's laws of motion are obeyed. But you may be asking, hey, Cher, isn't Newton's law of motion always obeyed? Yeah, that is true. Only if the frame itself is at uniform motion when compared to any other frame. So basically, what I mean is, hey, I can have any frame of reference. You're just going to say it's any coordinate axis. However, it's possible for us to choose moving objects as a frame of reference. So let's say instead of having my laboratory in VJC, I put my laboratory in Mr. Low's car, and Mr. Low is traveling at a uniform speed along the highway, and he takes measurements of different objects from his perspective. So he always assumes he's at rest, and the rest of the Singapore is at motion with respect to him. That's a legitimate frame of reference, right? Now the problem comes in if Mr. Low is not in a uniform motion car, but he is pressing on the accelerator. Once you are accelerating, you are in a non-inertial frame of reference. Why? Because from your point of view, everything else appears to be accelerating with respect to you. And if you draw a free body diagram of a falling object, you'll say, hey, there's only weight acting on it, right? Why is it making a curved path? Okay, the reason what we know why, right, is because the car is accelerating in the horizontal direction, not the falling object. But yet, to his point of view, the falling object takes a curved trajectory and therefore requires an additional force in the free body diagram to cause it to accelerate. So Mr. Low driving in an accelerating car, conducting experiments, that's a non-inertial frame of reference. Basically, we'll need an imaginary force to explain why other objects move in their path. So this means to say that frames of reference that are inertial are basically non-accelerating frames, but they can have a velocity. In fact, they must have a velocity because frames can move respect to one another with constant velocity and neither one is correct, right? They're all valid as long as they're not accelerating with respect to one another. So these are called inertial frames of reference. So one good example of an inertial frame of reference, right, is a merry-go-round. So let's say a person is in a merry-go-round, okay, and he has to explain his motion, right? So he's like, the whole world is moving around him, but everything is rotating. So the only way to explain it is that there's a centrifugal force, you know, to help him move in. To him, he's moving in a straight line. The world is rotating around him. So he has to invent this centrifugal force that pushes outwards on him in order to reconcile it with Newton's laws. However, if we have a point of view on the right, where we take the reference frame to be, say, the center of this rotating object, well, it's not accelerating. The center doesn't accelerate, right? So we can observe the person on the merry-go-round, and we can use Newton's law to explain it. He has a net force pointing towards the center. Therefore, that net force provides centripetal force. So therefore, he has to move in a circle. So that's an inertial frame of reference. So first example, pause it if you want to try it on your own, is calculate the centripetal acceleration of a point on the Earth's surface, which is close to the equator. So this is one of your standard H2 centripetal acceleration questions. I give you the radius of the Earth. So centripetal acceleration is v squared over r, right? So for the Earth, which rotates once every 24 hours, we can substitute the period by 24 hours and expand our equation. This gives us a equals to 0.034 meters per second. So a lot of times, actually, the Earth itself is not a inertial frame of reference because the Earth is rotating. So our point on top of the surface of the Earth is non-inertial. However, this acceleration is very small, so normally we neglect it and then we say that, oh, you know, a frame of reference on the surface of the Earth is an inertial frame. Alright, let's get into some mathematics. Let's assume that the velocity, let's define the relative velocity of A with respect to B as VAB. Okay, so the alphabet that comes later is the observer. The letter that comes first is the object that we are talking about, right? Actually, you should be familiar with this. This is in H2 physics. So the relative velocity of A with respect to B is VA minus VB. We know it. You always subtract the observer's velocity, correct? So very simple example. Taking to the right to be positive, we have a duck and a rabbit. The duck is moving to the left at 1 meters per second from the ground's frame of reference, and then the rabbit is moving to the right with 3 meters per second. So the velocity of the duck relative to the rabbit is the duck is moving away from the rabbit at 4 meters per second, but to the left. So since velocity is a vector, we have to take sign convention. This becomes minus 4 meters per second. What do you think the velocity of the duck with respect to the rabbit is? Well, if you guessed it's the negative of the previous answer, you are absolutely correct. So doing the calculation, VRD, velocity of the rabbit with respect to the duck, is the velocity of the rabbit subtract away the velocity of the duck. So you get 4 meters per second. So you can see that usually they are the negative of one another as long as neither is accelerating. However, problems in mathematics are usually not so simple. In real life, of course, we have three-dimensional motion and velocity is a vector. So in 2 dimensions, the same rule must apply. We will take relative velocity and then do geometry to find it. So let's say we got this man with a blue hat moving to the left, and we got this boy with a red t-shirt running in a y-axis direction, you know, upwards, I guess, in this frame of reference. What's the velocity of the man in the blue hat with respect to the boy? Well, we'll need to do vector subtraction. So VAB is VA minus VB. So we'll do the mathematics and use Pythagoras theorem to find the hypotenuse of this triangle, which turns out to be 5 meters per second. And then we have to completely define directions for vectors. So we'll take tangent theta and find that it's 53.1 degrees south of west. So from the boy's perspective, the man is running at a diagonal direction at 5 meters per second, 53.1 degrees south of west. So we can do this. We have done this in H2, right? So this is important because once we understand this, it's quite easy to translate into special relativity. So relative velocity is important, okay? It helps us transfer one reference frame to another. Okay. Now, before we get on to the next part, right, I have to discuss a definition for you. So let's say you celebrated your birthday, you had a birthday party. That's an event, right? To a lay person, what an event is very simple. However, in physics, it's a little bit more, we need to be more specific. Oh, you can't just say, oh, you know, we had an event yesterday. What was the event? Oh, it was my birthday and it lasted 3 hours and we did this. No. Physics, we don't call it that. An event is something that occurs at a particular time and a particular space. So an event is something like the start of the birthday party is at 8 a.m. at VJC. So then it is well defined. It has space axis, XYZ, and it has a particular time coordinate as well, right? So let's say I got two particles colliding, right? And then I can say, oh, you know, when their collision is specified at x equals to 3, y equals to 4, z equals to 5, and the time is at 6 seconds from some arbitrary starting time. So then it has a coordinate 3, 4, 5, 6. Right? So this is an event in physics. Alright, and once you send out your message to your friends to tell them, oh, you know, birthday party is happening this place, this time, right? unless they read the message wrongly, everybody can agree on that. This event is at this time at this place. So that's something about the property of events as how we understand it in physics. Alright, before we even get to anything in special relativity, we have to do what has already been done before. So Galileo, famous for showing that objects accelerate at the same rate regardless of their weight. When he dropped atoms from the Leaning Tower of Pisa, well, we give us Galilean transformation. So Galilean transformation allows us to transfer measurements in one frame to another. Pretty cool. Just using relative velocity, very easy. So let's say we have two frames, the S frame and the S prime frame. The S frame is at rest, and the S prime frame is moving with respect to the S frame at the velocity v in the x-axis. If I measure an explosion in the S frame as xyzt, what will be the coordinate in the S prime frame? X prime, Y prime, Z prime, T prime. So basically, I want to be able to relate X to X prime, Y to Y prime, Z to Z prime, and T to T prime. So for Y, Z, and T, because nothing changes between the two frames, it's very simple. Y remains at Y prime equals to Y, Z prime equals to Z, and T prime equals to T. However, because for the X coordinate, there is motion, so we will subtract away the relative velocity, the velocity of the moving frame's velocity. So to get the X coordinate, it will be X minus Vt. So it's using relative velocity. So not too difficult, right? Aside on certain physical properties, if we measure length in both frames, they'll be the same. So let's say we had a length of a stick. The length of a stick will be x2 minus x1 in the S frame. Right? That's how we measure length. Use a ruler, measure x2, measure x1, subtract it. Right? And in the S prime frame, it'll be x2 prime minus x1 prime. So let's check that you get the same length. We'll substitute x2 prime as x2 minus vt and x1 prime as x1 minus vt. So you see the vt's cancel out and you get back x2 minus x1. So length remains unchanged regardless of whether you're measuring length in the S frame or the moving S prime frame. So basically we can have this statement. Distances are invariant under Galilean transformation. Of course, nothing changed about the time. Time is the same in both axes. So the time intervals are also same. So two events that happen simultaneously in one reference frame are also observed as happening simultaneously in another reference frame. So basically, time coordinates always match even when we have frames moving with respect to one another. Okay, so this is the gist of Galilean transformation. So now you are equipped with this knowledge to be observers or convert your measurements in one laboratory to any other moving laboratory. Okay, let's take a quick try at example 2. We got a particular particle in the frame of reference S at x equals to 200, y equals to 5, z equals to 15. Then we have a frame, moving frame, S prime, and it's moving in the x direction at 20 meters per second. And at time t equals to t prime, at equals to 0, the origins coincide. So basically they start at the same time. They start the time at the same time. So we're supposed to determine the coordinate of a particle in the S prime frame that we defined earlier at t equals to 0, t equals to 2, and t equals to 3, t1 0, t2 5 seconds, and t3 15 seconds. So let's try this. So since the relative motion is only in the x-axis, we don't need to worry about the y-axis and the z-axis. They always stay the same. For t1, we'll check what the x-axis is. We'll have x prime 1 is x minus vt1. So since t is 0, it will still be 200 meters because they coincided at the start, the two frames. Right, at t equals to 2, 5 seconds, you just substitute t2 equals to 5 seconds, and then the distance is 100 meters. It's quite simple, right? Because the second frame that's moving is moving towards the object. So obviously, at a later time, it will measure a smaller distance. At time t3, you already move past the object's location. So x3 prime will be x minus vt3, and vt3 is just 15 seconds. You end up with minus 100 meters. So basically, the coordinate in one frame can easily be mapped into another once you know the relative speed of the two frames. So we have discussed coordinates and how to change coordinates. What if we are trying to convert velocities? So let's say I'm measuring the velocity in the S frame, and in the S prime frame, which is moving, I'll measure the velocity of a moving object as well. Right? Easily done. We just differentiate by time throughout for displacement, and we'll get the equations for velocity. Of course, you can imagine what we should get for acceleration, because the frames are not supposed to be accelerating with respect to one another. You should get the same acceleration for any frame. So anyway, focusing on just the x-axis, the velocity in the prime frame is dx prime dt. So we'll differentiate our x transformation, and dx dt gives us vx, and dv dt gives us velocity. So we just subtract away the velocity of the frame's motion. So try a simple example. A bus leaves a bus stop at a speed of 15 meters per second. There's a couple of observers we could have. We could have an observer at the bus stop. We could have an observer at of the student running after the bus, or we could have an observer in the bus. So the question says there's a desperate student chasing after the bus, and he moves at 3 meters per second with respect to the ground. What's the speed of the bus relative to the student? So I don't even need to use Galilean transformation, right? We can just use our relative velocity equation. We know the answer should be 12. But let's try. So look at option 2. We'll use the ground as the S frame, and we'll use the running student as the S prime frame. So Vx prime is Vx minus V. So 15 minus 3 gives us 12 meters per second. In fact, the Galilean transformation for velocity is how we got the relative velocity equations in the first place. Okay, so we did displacement, we did velocity, let's do acceleration. Acceleration under Galilean transformation. So although the frame itself is not accelerating, objects can accelerate in inertial frames, because we're just measuring objects, right? So the objects themselves are free to accelerate or move however they want. The frame itself cannot accelerate, alright, which means the coordinate axis cannot accelerate. So we said Newton's second law is invariant under Galilean transformation, which means if I measure acceleration of an object in the S frame, it should give me the acceleration of the object in the S prime frame. It should be the same regardless. Why? Because acceleration is due to forces, and Newton's second law must be true in every single reference frame that is inertial, regardless of how we transit from one frame to another using Galilean transformation. So we'll apply differentiation with respect to time for the x prime frame for velocity, and you end up with ax prime will always be ax, ay prime will always be ay, and az prime will always be az. So acceleration is always the same for Galilean transformation. So there's a difference for displacement, there's a difference for velocity, which is relative velocity equation, and then of course there's no difference for acceleration. However, we had a big problem, and this is where special relativity does come in. It's light. So unlike Newton's equations, right, Maxwell's equations explain wave behavior. They do not obey Galilean transformation. There's a speed of light c in Maxwell's equation, which is supposed to be 3 times 10 to the power 8 meters per second. And this speed of light comes from two constants, mu naught and epsilon naught, which you will learn in J2. One is basically the constant associated with electric field strength. The other is the constant associated with magnetic field strength. So basically light is electromagnetism, correct? So these two constants gives us the speed of light. But the speed with respect to which reference frame, Maxwell's equation doesn't take care of this, right? It's just the speed of light, it's fixed. It doesn't matter what frame of reference you're supposed to use. Wait, does this mean that the electromagnetism laws should not be the same for inertial frames? But why? The rest of the other Newton's laws are. So there is a slight problem reconciling these two, right? So let's do relative velocity for light then, with these two requirements together. So let's say I have a car and it's moving at night and it turns on its headlight. With respect to a person on the ground, right, I can do Galilean transformation for velocity. So the speed of light Vx is the speed of light with respect to the ground, and V prime is supposed to be c. So Vx, we can just add the velocities, right, and then we'll end up with a speed larger than the speed of light because I have to add up velocities. Yeah, so strange, right? So basically what this says is that regardless of whether you are sitting in a car measuring the speed of light and the car is moving, or you're standing on the ground looking at the car moving and the light is shining out of the car, both the speed of lights must be c. But shouldn't the person in the car see the light moving slightly slower because he's moving with the light? He should minus v, right? So that's the problem. it should both be C under Maxwell's equations, but it is not under Galilean transformation. So we have a contradiction. So Einstein's postulate solves this. So this is the proper special theory of relativity. Finally, right, after like half an hour, we can get to the actual theory of relativity. The rest is just, foundational stuff. So the first the first postulate, right, is the laws of physics are the same in all inertial frames of reference. So earlier on we were saying that, maybe Newton's laws are the same in all frames of reference. Now we're saying no. All laws of physics, including Maxwell's equations, should be the same in all frames of reference. Number two, the speed of light in vacuum has the same value in all inertial frames of reference, which means Maxwell's equations are correct. When there is a speed of light, it is correct. It's c in all reference frames. So that means the person sitting in the car measures the speed of light coming out of the car as c. The person standing on the ground also measures it as c. So that's the assumption. That's not the part to solve. The part we have to solve is then Galilean transformation. We gotta fix it. So back to events, right? The first consequence of special relativity is going to be a bit difficult to understand. Please rewind these slides again if you don't understand, or look for a YouTube video to discuss the simultaneity of events. Is, let's say I have two events, right, that occur, A and B. So each event should have its own x, y, z, t coordinates as measured from any observer. So let's say I have an observer and two events happen, like two explosions happen, right? They each have their own space-time coordinates. If they happen one after another, TA should be smaller than TB, right? Now, we can say that they are simultaneous if TA is TB. That means, of course, if the two timings match, right, that means they occur at the same time, obviously. So if two explosions have the same timing, they occur at the same time. It's like tautology like that, right? Alright students, let's take a quick look at this animation from a YouTube video that shows us how two events that can be simultaneous to one observer and yet not simultaneous to another observer. So in this setup, basically there's a train moving past the platform, and what the passenger
Imagine two observers, one seated in the center of a speeding train car,
standing on the platform sees,
and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time. So he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear.
He also predicts that his friend on the train will notice the front strike before the rear strike.
But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear. But her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct, within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
Both are correct, within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
So let's take a closer look at the situation. So we got Mavis, who's in a moving train. She's in the S prime frame, and Stanley, who's on the platform in the S frame. Okay. So the lightning bolts strike the two ends of the train A prime and B prime, A and B, which are on the track, right? Yep. All right. So what happens is from the perspective of the S frame, from Stanley's frame, he basically sees that the light waves move from the front of the car towards Mavis, and Mavis is moving towards them. So the light waves move at the speed of light, so Mavis will hit the front light waves first. So she should see, to his perspective, she should see the front light waves hit her first. But then, because he's standing at the platform, so these waves also travel to his eyes and travel at the same speed, the speed of light. And since he can work out backwards that they all travel at the speed of light, they also must have impacted A prime, B prime, B, and A at the same time coordinate t. So from Mavis' point of view, right, actually the two light waves hitting A prime and B prime both travel equal distances towards her because they are moving at the speed of light. However, from her point of view, it is not because the train is moving towards the light that results in her seeing event B happen first, and therefore she can work out backwards that it was at the same time, but rather her time coordinate for the lightning strike at B is at an earlier time than the lightning strike at A. So therefore, to her perspective, the light traveled towards her earlier, so therefore B must have happened earlier. However, from Stanley's point of view, the light from the two bolts arrive at the same time, so the bolts strike the front and back of the car simultaneously. So you might be wondering how can this happen, right? How can two events that are simultaneous in one frame happen not simultaneous in another frame, even though all that's different between the two frame of reference is that one of them is moving with respect to the other? This is because of the first postulate, right, which is that light moves at the same speed in all frames of reference. So what is different about the two frames? Well, to Mavis, actually the rest of the world is moving around her, right? So there is a relative velocity. So something like timing, the time coordinate of events can also be different because something else is different, right? There's relative velocity. However, for Stanley, he will see a different thing altogether, which is that the bolts are simultaneous. So they are both valid point of views. So what we think that is this uniform time coordinate that is the same for every person in the universe, well, it's different because like a person can have a position coordinate, time is also one of the coordinates. So because of special relativity, these time coordinates have to do a transformation when going from one frame of reference to the other. So we saw earlier on, right, in Galilean transformation that, hey, when we do transformation for moving frames, even for without special relativity, right, coordinates can change when we are going from one observer to another. So now with special relativity, time coordinates can also change when going from one observer to another. Generally, if an object is moving, further away events will appear to happen later than they should, relative to another frame that is not moving. Okay, so we can take a look at this example where something similar is happening. Basically, we got a spaceship, right? And it's traveling at velocity v to the right, and an explosion occurs in the middle of this spaceship. And you know, when there's an explosion, right, there's light coming up from the explosion. And since the explosion happens in the middle of the spaceship, this light will move to the right and move to the left of the spaceship, hitting these two mirrors. So for us, right, there's a couple of observers. One observer can be inside the spaceship moving, and the other observer can be outside, watching the spaceship move towards the right at speed v, and watching these light waves move towards the respective mirrors. So this example really tests if you understand the previous train example. Right, so let's you can pause the video to try if you want. So the question is, calculate the difference in time between event A, the light reaching mirror A, and event B, when the light reaches mirror B, from two perspectives, the observer in the spaceship and the observer outside the spaceship, and then comment on your answer. So let's talk about the observer in the spaceship. The observer in the spaceship, right, will see light traveling at a speed c towards each mirror and cover the same distance L. So to the observer in the spaceship, right, he will just say that, oh, you know, these two events are simultaneous, right? So the time difference is 0. Right, so to an observer at rest outside the spaceship, right, this light from the explosion still has to travel to the two mirrors, and the light actually won't travel a distance L because the back of the spaceship is moving towards the source. So we expect that this time should be shorter, and mirror B is at the front of the ship. The front of the ship is moving away from the source, right? So this time should be longer. So we can actually set up these equations. On the left hand side is just the speed of the light times the time TA to reach the mirror at the back of the ship, right? and we end up with TA equals to L over C plus V. Right, so this is a shorter time compared to mirror B, where the mirror is actually moving away from the source. So we have to add the speed of the ship in. Right, so the speed times time will tell you the distance that the ship moved in that amount of time, TB. So we can solve for TB and get L over C minus V. Right, which shows you that, hey, actually from the perspective of a person inside the spaceship, right, outside the spaceship, these two events happen at a different time. Now let's say the ship is traveling at 10% the speed of light, right, which is quite fast already, okay? So for such a thing to happen, right, and then we can just sub in some general dimensions of a spaceship, okay, say a 2-meter long spaceship, right? What you end up with a difference is just still a fraction of a second, right? So what we can conclude about it, right, is, you know, the time difference is very, very, very small, almost negligible, unless we talk about objects moving extremely fast. Let's say on a day-to-day level, right, we don't report and say, oh, you know, things are not simultaneous. Like for example, the teacher can be walking in the exam venue, and then the students are sitting still, and then a teacher say, oh, you know, it's time's up, and then the clock has a hand that reaches 12, and then all the students are supposed to put the pen down, and then you wouldn't say, oh, from the teacher's point of view, this is simultaneous, and the student's point of view, you know, they put down the pen late or something like that. That's because the difference is too negligible. It's too many zeros behind because the teacher's motion is you know, way smaller than the speed of light. So this effect is only noticeable when the difference when the speeds are actually closer to the speed of light. So the first phenomenon we observe, right, is that, hey, things that are simultaneous in one frame may not be simultaneous in another reference frame, and this is because the speed of light is fixed regardless of whether the frame is moving or not. When by right, normally, if under Galilean transformation, we will, you know, reduce the relative speed of light. So this is the effect of the first postulate of relativity. Then there are two more effects, right, which are very interesting, and these are classic telltale signs of you know, that the world is a bit weirder than we think about it because of certain rules, and we don't really see it on a day-to-day basis only because our speeds are relatively small compared to the speed of light, right? So the next two phenomena we'll take a look at is length contraction, where moving objects appear shorter in the direction that they're moving, and time dilation, where moving clocks appear to run slower than clocks in your own frame of reference when you're looking at an object that's moving. So first one, we take a look at time dilation. Basically, the tagline to remember is moving clocks run slow. So if you're looking at someone running and he has a clock or a watch on his hand, that clock or watch will run slower than your clock, which means 1 second for him appears to be longer than the 1 second that happens in your frame of reference. Right, so to set up this one actually is quite simple. It's again to do with the fact that the speed of light is fixed. Right, so we have Mavis and Stanley again, and Mavis is sitting inside a train and she's in an S prime frame. She has this little laser, right, that she shoots into the what's this called, ceiling, and the ceiling there's a mirror that reflects the laser back down. So we want to find this time interval T naught. Okay, so for her, right, how will she measure it? Well, she'll just take this laser, turn it on, it will travel the distance 2D, and then she will use that to measure this time interval. However, for Stanley, right, because he sees the motion of the train and the speed of light is still the same, it's still c, right? Now this distance that the light beam travels, right, will have to be longer. Why is it longer? Well, as the train moves to the right, right, the light beam has to travel a diagonal path with the length L and a diagonal path down with the length L again, right? So this is a longer distance for the light to travel, yet the light still has to travel at the same speed, c, right? So Stanley will conclude that, hey, for the light to bounce to the ceiling and come back to the source again, right, this actually takes a longer time, and the time taken should be longer than what Mavis will claim it will be, right? So this gives you a very good understanding of why the time reported will be different. It's just because that speed of light have to be same in both reference frame, even though there's actual motion between the reference frame. Right, so Mavis sitting on the train will carry out the experiment. She has a special clock. She can measure the time taken for the light pulse to leave the source and return, and she measures this time interval delta t prime. Now I'd like to stress now, right, that we're doing some sign conventions or some symbolic notations. So the prime frame, right, will always be the moving frame, and the non-prime frame will always be the rest frame that we are looking at in the question. Okay, anyway, let's put in what she measures into the algebra. So delta t prime, what the time that Mavis measures will be 2d over c. For Stanley, the time that he measures will be dependent on the distance that the light ray travels in this triangle, and you can use Pythagoras theorem to go and find it. Turns out that if you use Pythagoras theorem to find these distances, well, the distance that the light beam travels, ct delta t over 2 square, will be equal to d square, where d is the height of the train, plus v delta t over 2 square. So delta t is the time taken for this beam to go to the top and come back down in his frame of reference. So basically the unprimed frame is in the stationary frame. Okay, so the unprimed time is in the stationary frame, and if you make the delta t the subject, you will end up getting this equation 2d over square root c square minus v square. So c square minus v square, right, is a very important term that we'll use in special relativity. Why? Because we can take out 1 over c square, sorry, and then this fraction will turn into 1 minus v square over c square, and then that c square that we take out of the bracket, we can take it out of the square root as well. So it will become 2d over c, which looks like our previous expression, with this extra factor 1 over square root 1 minus v square over c square. Okay, so that's a very important factor. Right, so we'll compare the two values that we obtain, and it turns out that this extra factor of 1 minus v square over c square to the power of negative half, this we replace by this alphabet called gamma, and gamma is called the Lorentz factor. Right, so gamma is a Lorentz factor. Gamma is a number that depends on how fast the frames are moving relative to each other with respect scaled by c square. So of course, gamma takes on a particular value when v is the speed of light, and takes on another value when v is 0. So for two stationary frames. So let's take a look at how it behaves later on. Okay, we'll just continue with this example. The time interval for the light pulse to fire and be detected and measured by the observer of the train, delta t, so the person in the moving frame, will be different from the time measured by the observer on the track. So that's our conclusion. Right, let's take a look at gamma. So gamma is a number that's always greater than 1. Why? If I substitute v squared equals to speed of light, basically it will be 1 minus 1, which gives me 0, but 1 over square root, which basically gives you infinity. So if the object is moving at the speed of light, the Lorentz factor will be infinite. Right, what happens if the two frames are not moving with respect to one another? Then v will just be 0. So you get 0 over c squared, which is 0, and then 1 minus 0 is still 0, so 1 over square root 1 is still 1. So basically your Lorentz factor is 1 when the two objects have no relative speed. Then as you increase the relative speed by a little bit, so like for example 0.3 kilometers per second, you can see that the Lorentz factor increases slightly above 1 but very, very far away. Then you need to get very, very close to the speed of light. To let's say 10% the speed of light, the Lorentz factor is only 7.1. And 1%, what? This is 1% is 99% the speed of light. And then this 99.9 the speed of light, your Lorentz factor is only 22.4. So obviously, you can see that this Lorentz factor will begin to explode, and the time dilation effect, which scales how slow the clocks run, gets larger and larger and larger, the larger the value of gamma is, which means the larger the relative velocity between the two frames. So here I plot gamma versus speed of light. So you can see that gamma stays pretty flat all the way to until like maybe half the speed of light, then you get anything noticeable. So that's why in the day-to-day, we don't notice any time dilation. Right? However, if you have a very, very, very sensitive clocks, we have some called atomic clocks. They can track many, many, many decimal places. And you put one on the plane and one on the ground, we can actually find that there's a time dilation difference between these two clocks. Right? And this effect really goes up the faster you get closer to the speed of light. And at 1c, you just get infinite. So basically, this graph is asymptotical about the speed of light. The time interval measured by an observer moving with respect to a clock is greater than the time interval measured by an observer at rest with respect to the clock. So this effect is called time dilation. So this is called moving clocks run slow. So delta t prime, right? Remember that delta t prime is actually the time measured by the object that is moving. We call this the proper time. Okay, proper time is always measured in the frame of reference at rest in which an event takes place. So a moving clock runs slower than the clock at rest by a factor of gamma. So that's your Lorentz factor. So all physical, chemical, and biological processes slow down. It's not just clocks that slow down. Time itself slows down. So everything slows down, including whatever you have in your equations and all that. It will also appear to slow down, right? So all these processes will appear to slow down in the stationary clock. And in fact, something very strange happens. Time dilation is reversible. An observer in one frame will observe time dilation in another, but the reverse also happens. So an observer who is moving, let's say I'm in the spaceship, or back to the train scenario, I'm in a train, and my train is moving with a certain velocity, but I don't know that because to me, I'm always at rest with my own frame of reference. I'm looking at a person who is moving past me on the platform because my train is moving through the platform, right? So this person's watch will also appear to run slow. So it's actually a mirror effect. It's like a reversible effect. The person at the platform sees the time move slow for a person in the train, and the person in the train will see the time move slow for the person on the platform because they both have the same relative velocity. Pretty trippy, right? Now, if that is the case, right, then we can always ask, oh no, which is the proper time? Now, this experiment, right, with the source and the mirror being stationary, right, is stationary with respect to Mavis. So Mavis is where the event is happening. The event is moving together with Mavis. So to Mavis, she is the proper time. All right, and Stanley measures the longer time interval t. So Mavis will always have the t prime frame, and Stanley will have the t frame. So looking at our equation, the proper time is t prime. So where the event happens, that frame will be t prime. So the time dilation relationship is delta t equals to gamma delta t proper. So that's one way to remember it. And of course, this gamma factor is 1 over square root v square, 1 over square root 1 minus v square over c square. Okay, so that's your gamma. So let's practice using this proper time in example 5. We have a pendulum whose period is to be measured as 3 seconds in a reference frame, which is moving at 0.95 the speed of light with respect to a stationary observer. What's the period measured by the stationary observer? So basically, the pendulum is moving, right? And the pendulum is measured in the moving frame to be 3 seconds. Which one is proper time? The stationary observer or the 3 seconds? So the pendulum is an experiment carried out in the moving frame. So therefore, the 3 seconds is measured by the moving frame. So therefore, the 3 seconds is the proper time, right? The stationary observer will measure a longer time than 3 seconds. So let's check our calculation gives this result. So we can calculate the Lorentz factor first, gamma, 1 over square root 1 minus v square over c square. And then we substitute in the 0.95c into the factor here, and we get a Lorentz factor of 3.203. Then we can use our proper time equation. So delta t, the time measured by the stationary frame, equals to gamma times the proper time, the pendulum's timing measured by the moving frame. So what we have is delta t measured by the stationary observer turns out to be longer, 9.61 seconds as expected, because he sees that the moving clock runs more slowly than the moving clock does see its own self. So it turns out we do have actually verifiable experiments that show that time dilation happens, even though the effect of time dilation only happens when people and objects are close to the speed of light. So we have muons, which are a bit like electrons, but they are higher in mass. They're actually not found in nature at this energy level of the universe, but they can be produced in particle collisions. So muons are like electrons, but with more mass. So they're produced when high energy particles from space collide with our atoms in the upper atmosphere. Now, because Earth moves relative to the rest of the objects in space, and these particles can be ejected at very high energies from objects with nuclear reactions like our sun, for example. These muons have a very large velocity with respect to our atomic particles, so they collide with a lot of kinetic energy, right? Now, the thing is, muons actually only have a lifetime of about 2.2 microseconds, right? Which means by right, after they collide with the atoms in a high upper atmosphere, they should decay within 2.2 microseconds and should never ever reach the surface of the Earth. This is because, right, this amount of time is not long enough, even if they move close to the speed of light, to reach the surface of the Earth, right? They will only travel 600 meters, right? So the muons should not reach the Earth, right? However, this time, right, which is the lifetime, the time taken to decay, happens in the frame of reference of the muon. Large numbers of muons are actually detected from the Earth. So from an observer on the Earth, the muons have a lifetime of delta t, whereas the muons measure their own lifetime as the proper time, delta t prime, right? So if the muon speed is very, very large, let's say 0.99 c, then gamma factor is 7.1, then this 2.2 microseconds becomes 16 microseconds, which is actually long enough or high enough to reach the surface of the Earth or travel for about 4.8 kilometers, right? So funny things happen. From the muon's point of view, right, actually it is not that their time is now longer, because to them they have to measure proper time, but it's actually the distance that they have to travel appears to shrink. And this is actually what we'll study next, right? Length contraction. Now, earlier on we said that, hey, time dilation is relative. That means if you have time dilation measured by one person in a rest frame, we can always reverse who is the frame of reference and consider the person moving in the spaceship as the reference frame. Then he should see other people's time pass slower as well, which means to say that, let's say I have two twins, right? One is Abing and one is Alian, right? And one goes on a spaceship and he travels for 0.8 c. Then when Abing moves, right, Alian is on Earth and she should see this time dilation effect on Abing, right? So he should age more slowly. So when he comes back, right, he should appear to have a younger age than his twin that's left on Earth, right? So Abing and Alian are twins, right? And first we can do some calculation. When he returns back to Earth, how many years would have this other person aged, right? And the trip that he takes is a round trip of 20 light years, and he's traveling at 0.8 c, right? And how long would he have aged in the same period? So let's go do some calculation. So speed is distance over time. So in time, in years, will be the distance in light years divided by the fraction of c. So the time will be 25 years, right? So the person who stays on Earth, right, would experience 25 years passing for this entire trip to happen, to see her brother move off, fly in a spaceship, and come back. This trip would take 25 years. So she would age 25 years. However, from her point of view, Abing is in a moving frame of reference at 0.8 c, so he should measure proper time. So let's calculate what proper time is for him. So we'll take the time divided by the Lorentz factor, and actually we should expect this to be a shorter amount of time because there's time dilation, so we end up with 15 years. So from her point of view, he would have only aged 15 years, right? Now let's take a look at the twin paradox. The twin paradox, right, says that, hey, but from the brother's point of view, when he flies away, right, it is the Earth that's moving away from him at 0.8 c. So it is not him that is moving in the spaceship, but rather the Earth is moving relative to him in the spaceship. After all, there's no preferred frame of reference, right? So shouldn't he be the one that ages more and he sees the clock in his sister's frame of reference tick slower, therefore she experiences time dilation, and therefore she ends up being younger than him? Well, this should be true, right? However, this situation is not symmetrical because actually he's not always moving at 0.8 the speed of light with respect to her. His direction will change, right? In order to leave and return, one person has to accelerate during a part of the trip. So it turns out that the person who is on the spaceship has to move away from the Earth at 0.8 c, then he has to experience this turn effect, right? He has to slow down, stop, turn around, and come back to the Earth and go at 0.8 c again. So Einstein's results, right, is actually only made in inertial frame of references. That is when the frame of reference is unaccelerated, right? If he decelerates and reaccelerates again, that period in time in which he accelerates and decelerates, the Einstein's result will not be valid, right? So turns out that actually we can still keep track of what's happening on and assume that he instantly turns around, and even special relativity should still be able to account for the fact that this twins paradox can be resolved. So how can we resolve that this person appears to have age less than his twin that he left on Earth? Well, what we can create is what we call these world lines. On the y-axis, we create c times t, which is the time reference frame, the time axis, and on the x-axis, we create this distance. Now, the traveling twin, right, on the way out, right, would travel with a diagonal path because there's relative velocity, right? So these are simultaneity planes, times that are supposed to be simultaneous for both of them. And you can see, of course, time passes differently for the twin that is moving versus the twin that is staying still. However, once he turns around on the return trip, the speed changes direction, correct? So now we have a different line representing his speed. So the simultaneity frames suddenly increase. Well, so you can see that this big gap here in time happens when the twin turns around, assuming he's able to instantly turn around. So this accounts for the time difference, and then actually shows that the traveling twin, right, will have to age more than the stationary twin. So if you're not very sure about this twin effect thing, or what we call the twins paradox, do just Google a YouTube video on it. There are many YouTube videos that explain this better than I can. So once again, we take a look at the Lorentz factor gamma, and we can see that actually this relative velocity, right, that gives us any kind of time dilation, actually only matters when you're very close to the speed of light. So let's say I watch one of the fighter jets moving, right, and then I say, oh, you know, this uncle who's flying one of our jet planes, right? The jet plane is moving quite fast with respect to the ground at 0.3 kilometers per second, 300 meters per second. Speed of sound, quite fast already, right? But if you take it as a fraction of the speed of light, that's 10 to the minus 6 only. And this gives you a very small Lorentz vector. So how many digits are we in terms of time dilation? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 powers difference, whether you have a difference in time for 1 second compared to 1.00005 seconds, right? A bullet travels faster, even then it's still too many zeros to make a difference. So the time dilation for a bullet is too low, right? You need to get very close to the speed of light. Then 1 second will start to count as 22 seconds. Then that factor is pretty big. So there's a big time dilation factor. So the closer you are as a fraction of the speed of light, the larger this time dilation effect. And actually, it only really becomes noticeable after you cross this threshold of half the speed of light. So that's why we don't really see it in the day-to-day life. Alright, the next phenomenon we're going to study is length contraction. So length contraction, the tagline is moving objects appear short. So if you're a stationary observer, you look at an object that's moving, it will be contracted or shortened in the direction that it is moving. So any moving object suffers length contraction along the direction of motion, and the length contraction happens because its measurement itself depends on simultaneity, and simultaneity is relative, so is the measurement of length. So let us think of a moving train moving between stations A and B, okay, with respect to the Earth, and the distance between the stations is LP as measured by an observer on Earth. The time required to travel from A to B again is measured by an observer on Earth is delta T is LP over V. So to travel from point A to point B, as measured by a person on Earth, this time measurement is delta T, not the prime frame, because this is the frame in which the train is not moving, right? The object itself is not moving. So the length required is length AB, this is LP, and then we'll just use the velocity of the train, distance divided by speed to give us time. Right. Now, for the same journey, let's consider another observer who is on the train itself. So the train is the one moving between the 2 points, right? So the person in the train does an experiment. So he is the one measuring the proper time, delta TP, right? Or usually for the other slides we've used so far, we use T prime, right? That's fine. Then you measure the distance between A and B. The distance he measures is L. But he also knows that relative to him, the train is moving to the ground at relative speed V. So that time that he measures will be the length that the train has to travel divided by the speed of the train. Okay, or at least the speed at which the ground is moving away from him. Now we can apply the time dilation equation, delta T equals to gamma delta T proper. So we'll substitute delta t as LP over V and delta t proper as L over V, the one measured in the train frame of reference. And you'll end up finding that LP is equal to gamma delta L, right? And gamma is this Lorentz factor that is greater than 1 or greater. So L equals to LP over gamma, right? So LP is always larger than L because gamma is a number of 1 or greater. So what we can say is the length of a moving object, okay, is always measured to be shorter than when the object is at rest. So this says length contraction occurs only along the direction of motion, and we can then define the proper length LP of an object as the length measured in the inertial frame at rest with respect to that object which is at rest. So let's say I'm trying to measure the ground length. So I need to be at rest with respect to the ground in order to measure LP, the proper length. So as long as I'm moving, I will not get the correct length, or not say correct length, I'll get a different length from the proper length. What I'll get is a length contracted length as long as I'm moving with respect to it. So this also applies to objects, right? So let's say I'm on the ground, I'm at rest with respect to the ground. So I want to measure the length of a plane that is moving across. I will definitely measure a different mass from its proper length. So if I wanted to measure the length of a plane, which is moving, there's two possibilities, right? Number two, I'm in the moving plane. I'll just measure the length of the plane by walking up and down the plane, right? With a ruler, for example. Or I have to land the plane, come out of the plane, so now I'm at rest with respect to the plane and the ground is at rest with respect to the plane, and then we take a ruler and on the ground measure the length of the plane, right? Then we will get the proper length of the plane. Any other method of measuring the length of a plane, say by standing still on the ground and trying to use a ruler to measure the plane as it moves past, okay, assuming we could do that, will always give you a different length from the proper length of the plane, and we call it L, the length contracted length, right? You notice that I'm not supposed to use the word true length because length measurements is relative. So there's no one true length. There's only length when it is at rest or some other length relative to a moving observer. And neither of these perspectives are wrong, to say the least. It's just that one of it is proper length and another of it is length contracted length. So our formula for length contraction is the length measured, the contracted length, is the proper length over gamma. And if an object has length L proper when it's at rest, then when it moves with velocity v, its length will become L equals to LP over gamma. So the proper length is defined as the length of an object measured by someone who is relatively at rest relative to the object. And the length of an object measured in a reference frame that is moving with respect to the object will always give you less than the proper length. Let's try this with an example. Example 12 says there's a train with a proper length of 500 meters. That means when the train is stationary and I stand still beside the train and I try to measure its length, I'll get 500 meters. Now this train is passing through a 200-meter long tunnel, right? And the train speed is very, very great, so that from a perspective of someone on Earth, the train can fit the 200-meter long tunnel. Wow. Alright? So let's say this man is at rest on top of the mountain above the tunnel. Then he sees this very, very, very fast moving train. Now it's moving along the track, of course, which is inside the tunnel. So of course, if there is length contraction, it'll be contracted in that direction. So just as the front of the train, the engine of the train is about to emerge as the last car disappears in the end so that it just nice fits 200 meters, what speed must it be at so that it's length contracted to 200 meters? Right, so quite simple, right? We just need to set up the length contraction equation. So we have L equals to LP square root 1 minus V squared over C squared. Okay, then we'll substitute the proper length in, it's 500. We'll substitute the desired length contraction length in, 200. And then we'll obtain a speed which is 2.75 times 10 to the power of 8. So this is like more than 90% the speed of light. So this train has to move at more than 90% the speed of light in order to fit the tunnel. Right, so of course it's a very hypothetical train. It's not likely to exist. Right, so let's move on. We do a quick recap of what we have done. We have length contraction and time dilation. So the formula for length contraction is the contracted length is the proper length over gamma, and the time dilated time, t, is gamma times the proper time. Right, so you notice that one of them is divided by gamma, which makes it smaller. One of them is multiplied by gamma, which makes it larger. So gamma is the Lorentz factor 1 over square root 1 minus V squared over C squared. Okay, and it's a number greater than 1 to infinity. depending on how close to C you are. Now, we'll do the big chunk now, which is Lorentz transformation. So before that, we already studied Galilean transformation. Basically, Galilean transformation is just a transformation of coordinate axis using relative velocity, right? And just a quick recap, formulas look like this. Galilean transformation works very, very well for every single phenomenon that we can describe, except that when we have velocities approaching the speed of light. And then we get three effects, right? Our simultaneity of relativity, we get time dilation, and then we get length contraction. So this transformation between axes needs to take care of these three effects, right? So this is our old Galilean transformation equation. You notice that if the relative velocity between the two frames of reference is v, so you just, in order to transform from the x coordinate to the x prime coordinate, we just need to subtract away v times t. So in 1890, Lorentz developed a series of equations which help to solve this problem, right? Basically, you want to transit from one coordinate frame to another coordinate frame that is moving, but also being able to take into account speed of light. So some quick assumptions before we set it up. We'll assume that the two frames S and S prime each have a clock which reads 0 when their origins coincide. Okay? And the S prime frame moves only in the x direction with respect to the other frame, and the velocity it is in v, and it's a uniform velocity because if there's acceleration, it's non-inertial already. Then sometime later an event happens lah. So the event that happens in the original frame, S frame, is xyzt, and when it occurs in a prime frame, our coordinate will be x prime, y prime, z prime, t prime. So the origins of the two frames are separated by a distance vt after a time small t, right? And also, according to observers in the S frame, the distance x prime will have to be contracted by a factor of 1 over gamma because of length contraction. So my Galilean transformation will have to take into account this length contraction, right? So x will be equal to vt, the speed, right, multiplied by, normally we just add x prime. Now we have to add x prime over gamma because this is the length contracted length of x prime. Now we can make x prime the subject, which gives us the Lorentz transformation. So we make x prime the subject, you have gamma multiplied by x minus vt. So actually it looks quite similar, right? The old equation for Galilean transformation has just x minus vt, but now we have a gamma factor in front of the length contraction. Alright, now we've solved it already, right? This is good, isn't that all, right? You want to do a coordinate transformation between two frames, one is moving, one is not. Even with special relativity, all we need to do is multiply by a gamma. For the y direction, since nothing is changing, there's no velocity in the y direction, and the z direction, they will just remain the same as per normal. But to take into account simultaneity, right, then we have to also transform the time coordinate, and this one's a little bit more difficult. So we consider that this explosion has light that is radiating outwards from the origin of S and S prime as they pass. Alright, and the light spreads out in a sphere in each coordinate system. Now we're actually doing some kind of Pythagoras theorem thing here. In the S frame, the equation of this three-dimensional sphere is x prime plus x squared plus y squared plus z squared is c squared t squared. So because we have time as an axis, right? So ct is the radius of the sphere. Now, if we want to have the S prime frame, we will just get x prime square, y prime square, z prime square, and ct prime square, okay, to get the same radius. Now we'll rearrange the items on the left hand side equal to 0, and we'll equate the y-axis coordinates. So y prime is y and z prime is z, and what we are left with is the x and the t coordinates. Right, so the x coordinates, don't forget we have our transformation that we already did earlier. So we can transform the x prime frame to the x frame and eliminate x prime. Now, this gives us t's, right? So what I want to do is I want to be able to transform from small t to t prime. So I'll make t prime the subject, and what I will end up with is this reasonably complicated looking formula. So if I want to change time from one axis to another, a time coordinate, the time coordinate will shift by the original time minus vx over c squared, and there'll be a Lorentz factor gamma in front. So let's put it together. We have a comparison of the Galilean transformation equations and the Lorentz transformation equation put side by side. When we were transforming from one frame to another in using Galilean transformation, you just have to minus vt squared for the x-axis, everything else will stay the same, assuming we're moving along the x-axis. For the Lorentz transformation, the equation looks more or less the same, but there's a Lorentz factor in front of the coordinate transformation for length. But for the time one, it looks rather different. We have also multiplied by gamma, but we have to subtract minus v over c squared times x. Okay, now that we have these two, let's check one thing. Do the transformations revert back to Galilean when the speed is very small? Sure, let's try it, right? So for the length contraction, if v is very much smaller than c, then the Lorentz factor just reverts back to 1. So our x prime will be equal to 1 times x minus vt, which is back to our Galilean transformation. And here, look at the term for time. If this v is very small compared to c squared, this whole thing is 0, and gamma goes to 1. So it does reduce back to t prime equals to t. So the Lorentz equations will reduce back to Galilean transformation when the speed is very, very slow. So let's check that the Lorentz transformation is able to give us length contraction. So let's consider a spaceship in the S prime frame traveling at a speed v relative to an observer in the S frame. So the spaceship is the S prime frame and the observer is the S frame. So the head and tail of the position of the spaceship will be x prime 2 and x prime 1 in the prime frame, and in the S frame it is x1 and x2, right, at time t. So we'll find the proper length of the spaceship. LP will be x2 prime minus x1 prime. So we'll do the substitution of x2 prime and x1 prime using Lorentz transformation. So x2 prime becomes gamma x2 minus vt, and x1 prime will becomes gamma x1 minus vt. Right? And then you can multiply out and cancel out some of the terms. Basically the vt terms cancel out, and what we'll end up with is gamma x2 minus x1. But x2 minus x1 is just the length measured in the S frame, so this gives me L. So I get my Lorentz transformation equation. The proper length of the spaceship LP equals to gamma L. Let's also check Lorentz transformation gives us back our time dilation. So we take a clock at the position at the origin of the S prime frame, which reads t prime 0 as it passes through the S frame. So our proper time TP will be gamma delta t over minus vx over c squared. So this is our Lorentz transformation. And then we will expand gamma. And substitute x as v delta t. Next, let's tidy things up a bit. Take out delta t, we'll get 1 minus v squared over c squared. And 1 minus v squared over c squared divided by square root 1 minus v squared over c squared gives us square root 1 minus v squared over c squared. It's basically a divided by square root a gives you square root a. Right? And then this square root 1 minus v squared over c squared is 1 over gamma. So we get 1 over our Lorentz factor. So delta t is gamma times the proper time, which gives us back time dilation. Now, if we have Lorentz transformation, we can always do an inverse Lorentz transformation. So a Lorentz transformation basically means I take measurements in a non-prime frame and I want to convert it to the prime frame. What will be the new coordinates? So let's say I have coordinates in the prime frame already. If I want to convert it back to coordinates in the unprime frame, okay, into the observer that is standing relative to the moving frame, all we need to do is reverse the sum of these signs and then switch the primes around. But you can also just work it out manually. So you end up with this set of equations. Alright, now that we got Lorentz transformation out of the way, the remaining topics are about the equations for relativistic energy and relativistic momentum and mass energy equivalence. So we'll start with the simplest one. Okay, simplest from whatever point of view we can have, okay? So basically, we have this equation that says that mass and energy are equivalent. Of course, they are not equal because they have different units, right? They're different quantities. But there's a way of converting energy to mass and mass to energy, and the conversion rate is E equals to mc squared. So how did Einstein come up with this idea? Well, he imagined that we had an empty box. Right? So let's say we have an empty box. And the empty box is length L. Right? And you know, we can let the box emit a pulse of light from one side of the box. And we know light is made up of particles called photons, and we know how to calculate their energy. And energy of one photon is hf, the Planck's constant times the frequency. So since a photon has motion and energy, it also has momentum. So in order to conserve momentum, if a pulse of light is emitted to the left, to the right, then the box must move towards the left. So we take a look at part B here. A pulse of light is emitted to the right inside the box. The box must recoil towards the left in order to add up the total momentum to be 0. Now, when this light reaches the right hand side of the box, it's absorbed back by the box, okay? And then the box must come to a rest again. This is because the total momentum again must be 0. However, what happens is that the center of mass of this block must have moved, right? Because it moved, and then now it comes to a rest. However, this block is an isolated system, so no energy or momentum should have escaped. So how can the center of mass of the box be moved? Einstein got around this problem by suggesting that, hey, even light itself must carry mass, even though it is massless. So mass and energy are equivalent. So this bundle of light that moves with momentum carries energy as well. So if it carries energy as well, it's as if the box has split into two parts, the light part and the box part, and some of the mass of the box was imparted into the energy of the light, and therefore the light moving carries it away with some mass, so therefore the center of mass of the box can move, right? So if a body gives off energy in the form of any radiation, according to E equals to mc squared, then its mass must diminish by E over c squared. So a mass of a body is a measure of its energy content. So if you think about it in a day-to-day life, right, actually it makes sense. So each of us, we are cold, right? Sorry, we're not cold, we are warm creatures. And we know that warm creatures emit infrared radiation. And when we emit infrared radiation, this carries away energy from us. So we lose energy in that process, right? So if you're in a colder environment, you will emit radiation more than you absorb radiation from the environment, because the environment is a lower temperature from you, and this causes you to lose energy as a whole. But actually, not only are you losing energy, because energy in the form of electromagnetic radiation like infrared energy carries away some mass, actually your mass must decrease as well. So the mass of a body is a measure of its total energy content. In chemistry, right, we only consider energy changes associated with bonds and electron potentials. So now we're talking about particle physics already. So you can see that relativity starts with objects moving with certain speed, right? But now we have to consider the energy of subatomic particles. Now, speeds of electrons are not very fast, relatively speaking. Electrons, of course, are very, very fast, but nowhere near the speed of light. And the participants, the electrons, are never destroyed. So even in chemistry, there's not much mass energy consideration. Okay, however, there still is. It's just that it's very, very small to have been detected. So whenever, let's say we do chemical reactions, and then we emit some other form of energy like heat and light, right? Actually, by right, the total mass content of the remaining chemicals should decrease. But because the speed of the particles are so small, and no actual particles are destroyed, there's very, very, very little mass loss, and we can't detect this. So basically, whenever you have a form of bond that releases energy, actually the total mass of the system decreases. You'll learn this in J2 particle physics, okay, in nuclear physics. In particle physics, however, when we have whole atoms that can be destroyed and created from scratch, okay, by using very destructive processes like within a particle collider, accelerating them to close to the speed of light and knocking them together, we can see that entire particle masses can disappear, right, and be present as energy, which means that that energy must have some kind of mass equivalent. And to calculate the rest equivalent, we'll use this E equals to mc squared equation. So I'll give you a illustration. Let's say I have electrons. How much energy is the rest mass of just one tiny electron worth? We'll use E equals to mc squared, and we'll find out that it's actually 8.2 times 10 to the power minus 14 joules. It looks like a ridiculously little amount of energy, right? So let's invent this new form of new unit of energy called the electron volt. The electron volt is defined, right, as the amount of energy that one electron gets when it moves through a potential difference of 1 volt. So of course you take E times 1 volt, but E is 1.6 times 10 to the power minus 19 times 1 volt gives you 1.6 times 10 to the power minus 19 joules. Now if we express this original rest energy of the electron as a function of EV, you realize that the mass of an electron is 0.511 mega electron volts. Now when you accelerate electrons, right, generally they gain EV level of energy. Your ionization energy is in the magnitude of EV. This is mega EV, which means it's a huge amount of energy compared to the mass of one tiny electron. And basically, that's what happens in nuclear fission and nuclear fission. In nuclear fission and nuclear fission, right, these are nuclear reactions where a more massive particle decays into smaller particles, not decay, breaks up into smaller particles, or smaller particles or lighter particles like deuterium, helium merge together to form a slightly big, more massive particle like helium. In these events, right, although the total number of protons and neutrons remains the same, right, the products weigh differently from the sum of all the reactants. And that difference in mass, right, is actually what releases energy in nuclear fission, in our power plants and nuclear bombs, and nuclear fusion, which actually powers stars, right? So although you add up the number of protons and neutrons, they're still the same, but the neutron plus the helium weighs slightly less than the deuterium plus the tritium. So therefore, this difference in mass using E equals to mc squared is the released energy. So here's a graph that you will learn in JC2. On the left axis is something called binding energy per nucleon, and on the right axis is mass number. So when we go from 0 to 250, right, basically we are going up the periodic table, where we get elements that are more and more and more massive, right? So for example, iron is number 56 because it has 56 protons and neutrons, right? So up the y-axis we have binding energy per nucleon. So it turns out that we always require energy to break bonds. So to take a nucleus and separate it out into its constituents requires us to input energy. And when you form a nucleus from the resulting nucleons, you release energy. So it's still like chemistry, where breaking bonds requires you to put in energy, and forming bonds requires you to release energy. So for overall reaction, to know how much energy is absorbed or released, whether it's endothermic or exothermic, you have to check how much energy you need to break the bonds. Then you check how much energy you need to release when you form the bonds. If you release more than you require to break up, then it's an overall exothermic reaction. So in chemistry, the bonds are, electrostatic bonds, basically between atoms with positive and negative charges, correct? Because electrons are negatively charged and nuclei are positively charged. In subatomic particles, however, if you want to break up a subatomic particle, like a proton, the bonds you're breaking are between the gluons within the nucleus. Or pulling apart the protons and neutrons, the protons and neutrons are also attracted by that same force. So we're pulling apart protons and neutrons and protons and protons, which are attracted by the strong nuclear force. So let's say, if you take a look at this left-hand side of the graph, basically what it's trying to tell you is that when I try to combine lighter mass elements like helium and hydrogen to form heavier elements like lithium, okay, we tend to release more energy than we spend to break up the initial nuclei. If you look at the right hand side, you will notice that very gently, but there is still a noticeable trend. When you spend energy to break up a heavy nuclei, you release more energy to form a lighter nuclei. Now both of these converge at iron 56 because iron 56 is the most stable configuration of protons and neutrons. So if you want to break up iron 56 and form something heavier with the resultant, you will need to lose energy overall, giving you an endothermic reaction. Or if you want to break up iron and make something lighter, you'll also end up losing energy, and you need to give extra energy in order to do it, right? So basically, iron is the lightest nuclei per unit nucleon, right? This is because it's the most stable. So iron is at the top of this graph, means it's the most stable. So in stars, right, nuclear reactions, for example, it will fuse tritium and deuterium in order to form helium, and then after that you start forming carbon, oxygen, and all that, and this process will occur in very large stars in their cores until you can get to form iron. And then when you run out of iron, basically the star dies because you can't merge iron to form something more stable and release energy. You suddenly lose all of the energy that is powering the star to keep it up, right? So gravity will win and crush everything down into a supernova, right? So that's what happened in stars. Back on Earth, however, because we have heavier elements, okay, these heavier elements are formed during the supernova and spread through the rest of the universe, so therefore Earth formed with some of them inside our crust. When we dig it up, what we have are things like uranium, plutonium. When we break them up to form lighter nuclei like lead and ultimately iron, well, energy is released. So on the right hand side is how we get nuclear fission, and on the left hand side is how we get nuclear fusion. So there's actually a lot to study about this. I'm just giving you the very basics about it, but hope you are still interested at this stage. Alright, so that's it about mass energy equivalence. So this is the main way we extract energy using mass energy equivalence through subatomic particles. Right? There's no good way to say turn a brick into energy, right? You can't make a brick disappear and turn it into energy. The day we can do that, we'll solve all our energy problems. Okay, let's take a look at example 15, which is about nuclear decay. So nuclear decay occurs when you have an unstable nucleus, and over time an unstable nucleus can decay into lighter nuclei by emitting particles. So this one decays to lead. Polonium decays to lead by radioactivity. So on the left hand side on top it's its mass number, and its mass number decays by 4 because it emits an alpha particle, which is a helium nucleus, who has a mass number 4, 2 protons, 2 neutrons. Now, this piece of information is the rest mass, where it's given in terms of U, and you realize that a lot of decimal places are given because usually the amount of energy differs for the mass in terms of a very, very small number of decimal places in mass. So it's given also in terms of U, where U is what we call the unified atomic mass unit, which is 1.66 times 10 to the power of minus 27 kg. So in this question, we're supposed to calculate the energy associated with this change in mass. Right, so let's write out the equation for this nuclear decay. It's quite simple. The polonium decays into lead and helium. So we can find the change in mass with the masses given, and we find that the change in mass is 1.23 times 10 to the power minus 29 kilograms. So the equivalent change in energy using Einstein's equation is 1.11 times 10 to the power minus 12 joules, which it looks very small, but don't forget this is for just one particle decaying, and in a big sample of a kilogram, you have billions of particles, right? So as long as a couple of them decay at once, you're releasing a lot of energy. So that's why nuclear decay can be used to make power plants, right? And this equivalent in terms of MeV, which we are used to in terms of atomic powers, atomic energies, this is 7 mega electron volts, so significantly more energy than the mass of one electron disappearing. Alright, so we have discussed that mass and energy are equivalent, right? But what happens when a mass, which is stationary, starts to move or is given kinetic energy to move, right? What then happens to its total energy? We know the total energy will increase, but what happens to its mass? So we can say that the mass of a body actually measures its total energy content, and at rest, right, it is called rest mass, m naught. So m naught represents rest mass. So the rest mass energy E equals to m naught c squared. However, if a body of a body, if the kinetic energy of if the energy of a body increases, whether by gaining Ke or by having a rise in temperature, right, then this mass will increase. So of course, you can't say that about your running, because when you are running to give yourself Ke, you actually lose chemical potential energy. So it's not a net gain in energy. So your mass doesn't increase that way. In fact, your mass is actually decreasing because the conversion to chemical energy to kinetic energy is actually very inefficient for the human body. So technically your total energy decreases. Alright, so we have a new definition. Is m naught is called the rest mass energy. When a body starts to move, what it gains is called relativistic mass, or at least the new mass is called relativistic mass. So how is the relativistic mass compared to its old mass? Well, we just have a Lorentz factor gamma in front. You see, Lorentz factor is so convenient, right? It appears everywhere. So this new mass m is called the relativistic mass. So as the velocity of an object increases, its mass must also increase. So this actually makes sense for us because a body in motion will resist acceleration more and more and more. Day to day, this is negligible because gamma is very, very small. But using Newton's law, F equals to ma, you can see that as an object accelerates to a higher velocity, you require larger force to accelerate by the same amount. So it will have more mass, right, due to this relativistic mass. Linear momentum also has to be modified. So linear momentum must be conserved, right? So when we do momentum, if you want to have a new equation for momentum, the conservation of momentum must still apply. The linear momentum of an isolated system must be conserved, provided net external force is 0. Also, our equation for momentum relativistically must reduce back to our classical momentum for low speeds. So if you take a look at this chart here, we are plotting the momentum of an object, right, in terms of mc. Right, as velocity increases, right, according to Newtonian mechanics, right, you will just keep increasing your momentum, correct? Because you will just be your momentum is just mv. So if you're 0.2 c, then you just be 0.2 cm, correct, for your momentum. And as you increase, there will be a point in time where you're supposed to reach the speed of light and your momentum will just be mc. But we do know that Einstein's equation prevents us from reaching the speed of light because your relativistic mass keeps increasing, right? So what happens is the relativistic mass must also continuously increase and the speed of light should be an asymptote. So how should we get an equation that looks like this? Well, if your guess is that we will be using the Lorentz factor, you are absolutely right. The relativistic momentum for a particle at rest, mass m0, is given by P equals to m0 v over square root 1 minus v square over c square. So the relativistic momentum is just gamma times your rest mass momentum. Okay, the derivation is a bit too difficult for us to comprehend at this stage, but you will learn it in university. Next, we'll talk about energy. So relativistic energy, this one we can derive, right? We'll start with work done. So the work done on a particle by a force F is area under the force distance graph. And according to Newton's second law, the force is dp dt. So what we can do is find what dp dt is with our new relativistic momentum equation. So dp dt is d by dt of relativistic momentum. So it's just gamma mu, right? And m times u is m and u can both change with respect to time. Okay, so assuming that my mass stays the same, alright, then we'll do the du dt. Alright, but then the Lorentz factor also has a u term inside, so this one also needs to be differentiated. So this is the result of the differentiation. You can try to work it out on a piece of paper if you need convincing. Alright, and then we'll use dx equals to du dt to do a substitution and turn my entire integration of work done into in terms of du. So our limits of integration also change from 0 to u. Right, and then basically now I'm integrating with respect to u, and you can do that. And what you will end up having is work done is this complicated equation here. Alright, but don't worry, we're just using work done in this case so that we can use work energy theorem to find an expression for kinetic energy. So let's go to the next slide and then we'll see what we can do with this. Looks kind of familiar already, right? You see mc here and you see Lorentz factor, and then you see minus mc without the Lorentz factor. So the relativistic kinetic energy of an object is gamma minus 1 m0 c squared. Right? And for low speeds, this must translate back into kinetic energy. So it turns out that if the Lorentz factor goes to low speed, you will get 1 minus 1 m0 c squared. Right, but don't forget we have c squared here, so we've got to pop the c squared back into the equation. You will get half m0 v squared. So you got to try this on your own if you want to verify that it's true. Now if you realize this looks funny, right, like why is there a minus 1, right? Well, it turns out that hey, your total relativistic energy should include kinetic energy as part of its component. So basically the total energy an object possesses should be two parts. One part is due to its rest mass energy, which is m0 c squared, and the other part is due to its Ke, right? So it turns out that gamma m0 c squared is the total energy, and gamma minus 1 m0 c squared will be the Ke part, and 1 m0 c squared is the rest mass part. So we have total relativistic energy E equals to m0 c squared plus K. So you can put this together, you get a total relativistic energy of a particle, including its Ke, to be gamma m0 c squared. So it looks very beautiful because the gamma factor is just in front of the m0 c squared. But don't forget, this is not Ke, this is the total energy including your rest mass. Now we can combine the energy equation and the momentum equation to get this special relationship called the energy squared equals to m0 c squared plus p squared c squared. Now this is very, very special because now I can apply this equation to particles with no mass. You see? So like a photon we know has no mass, so m naught will be 0. If m naught is 0, does the photon have no energy? Obviously not. It has energy in the form of its momentum, p square c square. And does this equation make sense for objects that are not in motion? Sure, right? If it's not in motion, it has no momentum, then this second term disappears, and we are left with e squared equals to m naught c square squared. So you can square root both sides, and you end up back with our original equation, E equals to mc squared, which is just all rest mass energy. Okay, example 19 actually puts all these equations at work, so I would think it's a good time for you to just try one of these examples by hand and see whether you can calculate what is required. So part A, find the rest energy of a proton in MeV. Find the total energy of a proton that, if the total energy is 3 times its rest energy, what is the speed of the proton? Basically, its Ke is 2 m naught c squared, so you can use that equation to go and find the speed. Then determine the Ke of the proton in MeV, determine the proton's momentum, show that if the momentum doubles, Ke increases by a factor of 4, but not true in relativistic momentum. So let's see. First, we want to express the energy, the rest mass of a proton in terms of MeV. So we'll convert E naught into m naught c squared using E equals to mc squared. And then you end up with 1.5 times 10 to the minus 10 joules. We'll divide it by the electric charge to get it in terms of EV, and after convert to MeV. So this is our result for MeV. A lot of energy. Right, next, we want to see, the question tells us that the energy of this proton is 3 times its rest mass energy. So basically what it's trying to tell us is that gamma is 3. So if you solve this, you will end up getting V equals to square root 8 over 3c, which is about 0.943c. And of course, you can multiply out to get something very, very close to the speed of light. Last, let's find the kinetic energy. So we know the rest mass energy, the total energy, is E. This is equals to K plus rest mass energy. So we can make K the subject, and we get the total energy minus the rest mass energy, giving us 2 m naught c squared. So this is 1.88 times 10 to the power 3 MeV. And lastly, we want to find the momentum. So you use E squared equals to P squared C squared plus M naught squared C4. And then you can substitute E as 3M naught C squared and solve to get 2650 MeV over C. So this is a very common unit for momentum in particle physics, right? Because kg meter per second is just too small, it's too large a quantity for small particles. But these small particles actually have quite a lot of momentum, as you can see from this. So we'll scale it by C. Part E, we're supposed to prove using classical physics that when momentum doubles, Ke increases by 4 times. Well, that's quite easy because kinetic energy is P squared over 2m. So you can do this derivation yourself, but you'll end up with the equation that kinetic energy is P squared over 2m. So kinetic energy should be proportional to momentum squared. So of course, if momentum doubles, kinetic energy quadruples, yeah. Now, the equation for relativistic energy and momentum, not so simple, right? Because you got E squared equals to P squared C squared plus M squared C4, right? So we have this expression for the new momentum, 2 square root 8 m naught c squared over c. That's the new momentum that we calculated earlier. So we can calculate the new energy. The new energy is 5.7 m naught c squared. So the new kinetic energy is 4.41 times 10 to the power of 3. We already obtained the previous kinetic energy, which is 1.88 times 10 to the power of 3 MeV. So if you divide it, you won't get 4 times, you only get 2.35 times. Right, so I encourage you to try these calculations by yourself because you get to make use of some of these new relativistic equations. Right, last few expressions here for us to learn. Momentum and total energy. So relativistic momentum and total energy are related to each other by this equation. P over E is V over C squared. You can just take some of the equations before that and divide to get this expression. And we cannot use these expressions for photons. Why? Because for momentum is m naught V over okay, this is gamma, and E is gamma m naught c squared. You cannot find the energy of a photon using these two equations because the rest mass of a photon is 0. So you end up having 0 momentum, which we know is not true for photons. You know that it doesn't have 0 energy and 0 momentum. So we actually need to use the E squared equals to m squared c4 plus p squared c squared equation to be able to find the energy of a photon or any other massless particles. There are a couple. So we'll end up with this relationship for the energy of a photon, or if you have the energy of the photon, you can then calculate its momentum. Alright, let's take a look at example 20, our last example. So in this example, a pi meson, a type of elementary particle, at rest decays in 10 to the power of minus 16 seconds into 2 photons. So basically the entire mass of the meson disappears and 2 photons take its place, and this happens for very, very unstable particles. Alright, so the meson has a rest mass energy of 135 MeV, so they already tell you the rest mass energy, and of course photons are particles of light that have 0 rest mass. So we're supposed to write an equation down for this decay, then find the energy of the 2 photons, they should have equal energy, and then find the momentum of the 2 photons. So let's get into it. So of course, very simply, the pi meson decays into 2 gamma particles. So basically the word gamma symbolizes photons. So of course we don't know what energy these photons are, so we just write gamma as a symbol for light, photons of light. Right, so since 2 photons appear, and each photon carries away momentum, and the initial meson is at rest, so according to Newton's second law, we need to conserve momentum, so each photon should possess the same momentum. But we know that for photons, their momentum is related to their energy, so they must have equal energy. So we can just divide this by 2 to get each photon's energy. Lastly, we can go and calculate the momentum of the photons. So the momentum of photons P equals to E over C from our E squared equals to P squared C squared plus M squared C4 equation, and obtain the momentum, which is 67.5 MeV over C, or if you want to convert kg to kg meter per second, you get 3.6 times 10 to the power minus 20. Alright, that's the end. So of course in this topic I can't cover every single part of relativity, or I can only cover some detail each part, but I hope you focus on some of these main sections, which is the equations for relativistic mass, energy, total energy, kinetic energy, momentum, as well as the energy mass equivalence. Okay, in another section, we also covered the Galilean and Lorentz transformation equations, so you have to learn how to use these as well. And finally, the three phenomena that we discussed due to special relativity and the 2 postulates of special relativity. So the 3 phenomena are the simultaneity of relativity, the time dilation, and the length contraction. So be ready to use all these equations for the Olympiad test. Right, I bid you all the best, and I hope that your experience and this Olympiad training has been good so far and you have learned a lot in physics. If you really love physics, next year you can still consider taking H3 physics, and some of these topics will also be in H3 physics, so you'll be well positioned to take them.